I should state that obviously this work comes out of two groups that are working together. Most of us are in both groups. So the first is the plastic collaboration, who you heard about this morning from Gautam's talk, and also the alerts topical team within the Dark Energy Science collaboration, because we know that we have multiple parts of the pipeline that we really want to, as the Dark Energy Science collaboration, understand and be involved in. The first is being part of simulating the alerts so that we can all help train your algorithms and your alert brokers, and then also making sure once you have done your work that we can ingest the way the brokers are handling things, the classifications, and then see how they impact our cosmology and how we kind of understand that. One of the big things in the Plastic version 1 was assigning a score based on how well people performed, and so we're going to be iterating on that as well as we go forward for Plastic version 2. We won't discuss that in detail now. This is something that Alex, Kim, and others are leading, but we'll start just talking about the first part of the process. You saw the overview from Gautam, and that's really useful to think through the things that we need to do. I'm going to run you through, in the second part of our demo, just run you through a demonstration of actually going from SNL simulations to an alert that can be then piped into a stream and ingested by the brokers. But in order to do that, we had to solve the problem, which was outlined of how do we take a small number of galaxies that we have a lot of information on, supernova hosts, for example, from a range of different surveys, and how do we make sure that we can port those to simulations at large volume? And so I'll hand over to Alex Galliano, who will take us through that first part of the process.
Yeah, thanks so much, Renee, for that thorough introduction. I feel like that introduced this notebook really well. So, hi, everyone. I'm Alex Galliano. I'm an NSF fellow at University of Illinois, and I'm going to be demonstrating some of the utilities of the code PLAsTiCC2, which actually comes out of the PhotoZ working group within DESC. But Martine Locken and I have been adapting it on behalf of the alerts topical team, like Renee mentioned, and we've been using it to generate more realistic host galaxy properties to include in the version 2 simulated alert stream. PLAsTiCC2 uses normalizing flows, which are a machine learning tool that allows us to predict a function that maps a very simple latent distribution like a Gaussian to a more complex multidimensional distribution like that corresponding to a multidimensional parameter space, in this case, associated with the properties of the CosmoDC2 galaxies. And the value of doing this is that we can then sample from a set of correlated properties to generate new objects or events that still have the same correlations as are seen within our original data set. So as Gautam mentioned at the beginning of the day, we're using the synthetic sky catalog CosmoDC2 to create our simulated alert stream and to kind of scale up from the small number of transients that have actually been observed. But there are some non-physical artifacts in the DC2 data that we're not looking to propagate through to our final data set that'll go into the alert stream. And so this is where PLAsTiCC2 really comes in handy, because we can sample new properties and remove some of this non-physical structure on a faster time scale than is, I think, currently planned for resolving this at the catalog level. So this is just a quick little tutorial that demonstrates how to do that. You can see we download PLAsTiCC2, and we also download a small subset. This is just 100,000 randomly sampled galaxies from CosmoDC2. And you can see that this version of the catalog that we've downloaded has, let's see, it has some shape information like Sursic index and light profile radius. It has redshift, it has star formation rate. Some of these will be in the final alert stream, some of them are not, but we're still going to be using them in order to generate our resampled properties for these galaxies and to make sure we're doing that realistically. Okay, so within PLAsTiCC2, we generate what's called a conditional flow. And so that's a flow that allows us to generate new properties. In this case, we're regenerating redshift and star formation rate, and we're conditioning it on other properties of those galaxies. And so this methodology takes what's called a bijector, which is just the function that maps from the simple latent space to the parameter space. So here you define a bijector and the columns that you want to condition on, as well as the new columns that we're trying to generate, in this case, redshift and star formation rate of the galaxy, which, as we've mentioned, show kind of unphysical structure in DC2. So we can construct the flow and train it. We plot the training losses here. It seems like it trained relatively well. It's trying to minimize the loss as best as possible. And so this is really the meat of the algorithm here, where we sample for the new properties. So n, you can generate n number of samples for a set of conditioned properties, and we're conditioning fully on the data. So we want to generate one new redshift and one new star formation rate for each of the galaxies within our data set. And so just to plot a quick histogram comparing the redshifts associated with original Cosmo DC2 in green here, and then are resampled in orange here, and we see that it pretty faithfully reproduces the distribution between the range 0 and 1. We've just truncated it at 1 in our small sample, which is also part of the reason why it struggles a little bit right at the boundary, because we have a sharp cutoff. But other than that, it pretty faithfully reproduces our original redshift range. And so now we can plot the colors as a function of redshifts for A, our original DC2 galaxies, and B, our oversampled PZ flow redshifts. And the nice thing about this is that you can see that this kind of large scale structure that is physical and correlated that we want to retain in DC2 is really captured accurately by PZ flow. And this is a little bit harder to see in the small catalog, but you'll just have to maybe squint your eyes and trust me here, that you can see some of the tracks here that are non-physical within original DC2. These are unphysical correlations in color space of the galaxies. And those streaks are not preserved because of the scale of the correlations within our PZ flow oversampled properties. So this is really valuable. And in addition to oversampling these properties, one of the things that we want to extend in PLAsTiC version 2 is more realistically dealing with photometric redshifts. So technically, redshift was something that was included in PLAsTiC version 1, but it wasn't derived from photometry. So it's been said that it was too realistic, that it maybe gave teams more information than they would actually have in the alert stream. And many improvements have been made to our PhotoZ models since version 1. And updated PhotoZ models are going to be used to provide PhotoZ estimates in the LSST alert stream. So we want to make sure that we're providing realistic PhotoZs in our simulated PLAsTiC version 2 alert stream as well. And in this case, PZ flow also comes in handy here, because you can use it to condition redshift on the photometric properties of a galaxy and then generate new redshifts, which are essentially now photometric redshift estimates. So this is something that I'm showing off in the second part of the notebook. Just real quickly, from the previous example, we wanted to make sure that we're not changing the redshifts too much, so that we're not placing a particular galaxy at a completely different distance away from us, in which case some of the other properties of it might be non-physical as well. And so we just real quickly plot up the difference between the redshift predicted from PZ flow and the redshift seen in DC2. And you can see that the vast majority of galaxies have been shifted by less than a redshift of 0.1. So this is reassuring that we're actually doing something realistic here. So now we're going to move on to the PhotoZ estimation part. And I'm constructing two normalizing flows. One is from the original data set, the original photometry and redshift values, and the second with the oversampled redshifts and the apparent photometry if you were to place those galaxies at these new oversampled redshifts. And so let's see, I already went through the construction of the bijectors, so I don't need to talk about that again, but we build our two respective flows and train them. We see that the losses here are fairly comparable. And then we can generate posterior distributions across a particular grid in Redshift. So here we're just doing it between 0 and 1 with a bin of 0.01. And we estimate the photo Z as the location of the maximum in this posterior distribution for each of the galaxies. So now we have photo Z estimates both from our original DC2 galaxies and with our oversampled, quote unquote, true redshifts in PZ Flow. And this is how we do, as a quick example of the photometric estimations using the DC2 true redshifts. But then when we use the oversampled properties, as we did earlier, we see we get a much tighter distribution that doesn't have some of this unphysical structure within the correlation here. So this is also really reassuring, and the ability of PZ Flow to quickly generate posterior distributions for lots of different galaxies, like the simulated ones that we're going to have from Cosmo DC2, is one of the tools that we're going to leverage to place host information realistically within the version 2 alert stream. So then just at the end of the notebook, we save our properties, we do a couple of quick quality cuts. We see that 99.8% of DC2 galaxies were preserved after the quality cuts. So the not much unphysical information is thrown within there, and then we save. So I have thrown up this notebook, and hopefully it will prove useful, even if the individual broker teams are not going to be doing any of these validation efforts themselves. It turns out the code PZ Flow has proven very versatile and represents now a pivotal piece in validating our efforts for the alert stream. So I think that other teams might find it useful for lots of different purposes as well. And I think now Renée is going to talk a little bit more about how to construct the actual alert streams from the properties once you go from the catalog level information here to simulating individual transients with SNANA, and then the properties within SNANA with host information to the simulated alert stream for version 2.
I will indeed. Thanks. Thanks so much, Alex. I think that's a nice jumping off point. I should also say we are developing the kind of alert simulation pipeline within the PLAsTiCC alerts repo. So the demo is essentially one I've just put in the chat as well. And so I'm just going to take you through an example of just simulating one alert from the SNANA simulation. So just a recap, Alex generates redshifts and other host properties for the hosts from matching to Ghost and from using PZ Flow. And then we have a library that we can input into the SNANA simulations that will generate a bunch of different supernovae with their hosts properties as well. So that's the output that we then get from SNANA is typically a header file that gives you all the information for a bunch of different objects of a type of certain model class, and then also the photometric light curve files as well for those objects. This little notebook is heavily based on the LSST alert packet software, obviously, and also some codes for like reading and engaging with the alert packets themselves. So the first thing that we're going to do is we're just going to define some files that will read and plot the successful alert packets once we've generated them. So that's just some technical stuff. But the first jumping off point is that in this example, we couldn't use the currently defined LSST alert schema, which doesn't include this information. Now, of course, the alert schema is being developed, and some additional information will be provided in future in the final LSST alert schema. But for now, we really want to just make our own PLAsTiCC alert schema that has the ability to have whatever properties we want. For the purposes of this example, I've been super exhaustive, and we've edited the alert schema to have just everything that comes out of the SNN file. Of course, this is unrealistic and not something that we'll do, but let's just see what is in the alert schema. I should also say, if you go to the PLAsTiCC alerts GitHub repo, you'll see an example of this. You'll see an example of the original LSST current LSST alert schema version 4.0, and then you'll see my modification version 4.1, which is useful if you, like me, just want to kind of hack around a little bit as well. The additional piece of information related to this example is when we started thinking about this initially, we thought, oh, okay, we would take an existing alert and then make changes once the alert was formed, but actually it's much more simple than that. Given a particular schema, the actual fields can just be read in as an example, a JSON dictionary file, and then you can modify that dictionary with your own entries, and that's what we're going to do. So what does the alert schema look like in the first place? So the alert has one DAI source object typically, and then it has embedded within that DAI source object, sorry, DAI source, it has the previous DAI sources. So this is telling you what is the DAI source right now, and then what are the previous sources associated with this one DAI object. And that's what we'll be reading in. So it has some stuff you would expect, a source ID, RA deck, etc. Some properties that relate just to the flux. And then this is just giving you the information about the DAI source itself. And then we've added to it these additional properties, log mass, star formation rate, ellipticity size, the magnitudes of the host galaxies, etc. And as I said, this is sort of more exhaustive than we will be provided. But the nice thing about this schema modification is that now we can interact directly with, as we iterate on what the brokers will be getting and what is useful, we can adjust these simulations accordingly. So just to recap, we've got the DI source, and then inside that is the previous DI sources as another key. And you can kind of see that they're just replications of what the other DI source dictionary, just repeated now. And the thing that changes in each case is really the epoch or the MJD. And so this is what we want to reproduce for our SNN simulations. So what we do is we first need to pull the information from SNN. So SNN, as I said, has two FITS files basically in chunks. Basically, it adds a bunch of light curves into a photometric FITS file, and then it has a header file which talks about all the objects. For this example, we're just going to pick one object from one model where Alex has already used this PZ Flow to generate a host library and then simulated SNN with these host properties inside it. The first thing we need to do is we are going to pull off all the stuff from the photometry file. So this is FOT1, including the filter in any particular epoch, and then the flux and the calibration, the error on the flux. And then we compute an SNR, and then we have the MJD of that observation. There are also host properties that need to be associated at each time with this object, because we know we have one object from a particular model. And so we are essentially to each DI source assigning the host properties. In this case, I've added the typical ones, right ascension declination, and then these are the things that come from Alex's and Martine's work, the log mass, star formation, ellipticity, and then the magnitudes of the host. And then once you query this function, it returns you a little DI source that we're going to package into the alert at each step. So what we do after doing a little bit of porting of files is for each point in the light curve, I'll run to the place where it makes sense. So in this case, I'm doing it just for the G-band light curve for simplicity. But what I do at each step is I take the information from the SNN photometry and header file for this particular epoch. I'm going to iterate through the light curve, and then I create a DIS source, and then I append that DIS source into the list of previous DI sources and do this iteratively until I get the whole light curve in one alert. So it's actually super simple. And then what I need to do is I need to package that in schema. So now the alert contains within it all the light curve data, all the previous sources for that one particular band. We don't have to do that. Of course, we could just we know that you will have multiple different bands within a different alert, but in this case, we just wanted to make things pretty simple. And then you serialize the alert and you write it out to just an Avro object. for this example, we've just done one model, one alert at a time. But what we will eventually be doing is generating this in a stream. Once we have saved the models, so this is just a plot showing all the magnitudes, the source magnitudes generated across all bands. Now, there are some objects in the SNN file that either don't have enough data or the photometry flag, they really weren't detected. We need to have a way of throwing those out so that we don't waste a lot of time generating empty alerts. And so we do this in a very clunky way in this example notebook, just so that we can see what's happening. And then we write out the valid ones to file. But what we want to do once we've written them to file is, of course, to read them back. And so there's a little bit of functionality just to read in an alert schema. And now we can plot the light curve that we just sent out relative to some, normalized magnitude. So this notebook, we've actually included the SNN file, the photometry file, and the header file for these models. And so if you want to just have a play and just see what your alerts might look like and how to engage with them, please take a look at the GitHub repo, and I'll add it after the workshop. We'll add it to the generalized repo. But what are the challenges? What are the things that we're doing next? Obviously, we can't be
9 minutes, Renée.
Sorry?
9 minutes.
Okay, no problem. I'll be finished with lots of time for questions, yeah. So just to make, we don't want to be doing this in a Jupyter notebook and generating, tiny little, having a whole code run one alert. Of course, we want to do this in batches and do it really fast. And so the next challenge that we have is, first of all, ingesting these light curves a little bit more rapidly, generating the alerts at mixed bands, and making sure that we are correctly simulating them, and then realizing, okay, now that we have individual alerts, we need to simulate a stream. We need to be able to communicate and send that stream to the brokers. This is something we've been chatting about, making sure we can do that. And then hopefully by the time the challenge starts in the summer, you'll be able to get a stream that has all these different objects for all of the plastic models. We won't obviously identify them by the model in the case of the challenge, but you'll then be able to get a stream and have to classify them and know that they really come from a bunch of different realistic classes. And we can start to investigate, how does your ability to classify really depend on the alerts themselves rather than just the models specifically. And that will reach our main goal with PLAsTiC version 2.0 is how fast can you classify these objects with good certainty, because of course that's super critical if we think about follow-up, which we've been talking about a lot this meeting. So this was a super quick run through of the demo. Please take a look at it. And I'm super interested in additional comments and thoughts about, what you think you'll need and what tests you yourselves want to do of your brokers with the alerts. We had a conversation, obviously based on the slide that Gautam showed, about whether or not postage stamps would be useful for you to sort of see real versus fake. And so this would be a great time just to hear from the brokers how we can best challenge you in the challenge. So thanks.
Thank you very much. Yeah, so we have like around 7 minutes for questions. So I don't see any on the Slack right now. Please. I mean, one question that is related, well, to the previous talk on PLAsTiC was whether there is going to be more attention to the balance of the different classes, not to the balance, but to the realistic populations of the different classes. And I think Gautam is going to answer, in fact.
So I actually messaged this on Slack as well, but to some extent, yes. But there are classes like kilonova, which if you use the real rate, well, you'll get 1 kilonova in 5 years, and that's just not fun. So you should expect those to be augmented so you have a significant sample in the data set. But this is something we can do in consultation with the teams. If you want a sim that has perfectly realistic rates for every single class, we can make that. Just let us know. I also want to emphasize one other point here. We've been talking about this for testing brokers, developing ML codes, etc. And so this is a lot of like, pre-preparatory for LSST work. But even during LSST operations, this infrastructure is useful and important. If you are a broker team and need to evaluate your selection function as a function of time, you want to be able to inject fake alerts into the stream. This is all what this is for.
Yeah, there's nothing LSST specific about the simulations,
Yep.
other than we ran them for LSST cadence, but we can do that trivially. Yeah.
For any survey, in fact, if you notice in the notebook that Renée showed, the files that she was using are actually from ZTF. So any new survey whatsoever that comes on that you are doing complementary observations to LSST with, you can train your ML code for.
Thank you. There is a question also about the release. When it said this summer, if you can be more specific hemisphere-wise, and also if that means August, or what does that mean?
I'm sorry, that's a really good point. Yeah, I'm from the Southern Hemisphere, so I should know better. Go ahead, Gata.
So like where we are right now is generating these alerts, and then we want to send a sample to Eric Bellman Company at LSSTAP, and make sure that they are okay with it, and do sort of a test run of sending out the alerts to some of the brokers through ZADs. Assuming that that all works, it literally will take us a couple of days to generate the full sample. So we can ramp up very, very quickly. But I think this is again a thing that we would like to hear from broker teams about. You have to create a database to store these things. You have to make sure you have enough disk space. It's not a huge amount, but it's still a lot of pain and infrastructure development that has to happen on the broker side. So when in the Northern Hemisphere summer, would you like us to run this challenge? And if the feedback from all the broker teams is, oh my God, we're not really ready for this, can you please push this back a month or something? Fine, we can do that. That's why we're here.
Maybe we won't launch in August, given that many people are not around, but.
Yeah.
Yeah, I mean, my point is I think the challenge is most successful if we know what the deadline is. And I'm totally sympathetic to, like, it's really hard to meet specific things, but like this specific thing is what I am thinking about right now. Presumably all the brokers are listening to ZTF. So it's just a scaling question from them. You said earlier to let you know, okay, I think everyone's let you know, but like I still learn things every time I hear a PLAsTiCC2 challenge talk. So when will I know, and how much advance notice will that be?
Yeah, I think that's a really good point. I mean, we have a Dark Energy Science collaboration meeting coming up in July, and we had it nominally projected that we would be able to launch the challenge in July, because we're ramping up, but our simulations on all fronts are proceeding. I don't necessarily want to say, oh, well, July 15th, you can celebrate French Independence Day. Oh, I'm sorry, Bastille Day. There's no French independence, and then you'll get an alert stream. But that's the typical timeline.
So July 14th, but
exactly.
So Michael,
I heard you say not May or June.
Yeah. So Michael, I mean, part of the challenge here is the team that's working on this entire massive infrastructure is pretty much on this call. It's a very small group, and so that's really the constraint here. Is just if something comes up, we want to be able to adjust things by 1 to 2 weeks yet. We'll send out a blast, an email blast and Slack blast, and say once we have a little bit more connection with LSSTAP and Eric in particular, I think that's the key step. Is really once he is convinced that he can use the LSSTAP infrastructure to broadcast these alerts, we'll have a much more realistic projection of when we can actually do this challenge.
I mean, I guess I made my point, but you're asking for a challenge that'll be some finite period of time, a month or 2 months or something, and we need to schedule effort for that time.
Great.
And if we don't, then like we're not gonna get the best out of it. That's all I'm saying. I understand all the constraints and all the challenges.
Yeah. And this is why we've been engaging with the broker teams as much as possible, including you folks at for the PIT team. So Daniel Pettifort's, of course, been on a lot of these telecons, and it should be on everybody's radar to at least sort of plan for something around midsummer.
Sorry to jump in, but there is also another question, whether on the format, whether there will be a one topic stream available at some point, a continuous stream during some time frame, or if it will be split into training and validation streams.
We can send you the training data without a stream. We can just dump that into flat files and send that to you. as is like we did for Plastic version 1. And presumably we'll do that much before the challenge actually runs. So you have a chance to run your classifiers or retrain your classifiers as you need to test things. Michael is right. The real stream will go out as topics, probably topics by night. There'll probably be something like a week worth of history topics on the Kafka server. So if something happens to your broker during the actual challenge, you should be able to recover as long as you're back on within a week. So all of this, it should look a lot like just working with real ZTF data right now, just with simulated LSSTC instead.
Thank you. Before Franz and Alex, sorry, but there was another question in Slack by Paula regarding the metrics. How are you going to evaluate, what kind of benchmark metrics are you going to use to evaluate the performance of the brokers?
This is a wonderful question that is still under active discussion with Ashish and company. We've collected a bunch of potential metrics in a document that Alex can circulate. But we're open to other feedback. If broker teams want to highlight an aspect of their performance that we're not currently capturing, let us know. And I think a good place to do this is in Alex Kim's DIA topical team telecons, which have most of the broker teams attending, including Franz and others.
Yeah, and we'll also be bringing this up frequently in the TVS group so that we get a better understanding of the coverage in particular.
Thank you.
And again, like this challenge is not, it's just to get the science collaborations and broker teams working together. It is not to say this broker is the best broker because it did blah, blah by one silly metric. That's not the point.
And in fact, it's right now, I feel slightly opposite, that most brokers are more alike than like each other than they should be different.
Franz Bauer?
Yeah, so it would be useful to coordinate with Eric Bellum because he has a group of alerts that he's going to dump out that are from the project, from hits, cycle through. So these things shouldn't be at the same time because the brokers really do have to deal with the ones from Eric as part of their evaluation, right? So it would be good to coordinate when you drop plastic so it's not right on top of that.
That's a very good point. Alex?
Yeah, so I'll just mention a couple of things. One, referring to a previous question. There are two classes of evaluation metrics that we're looking at. One of them I would say is more technical, like latent time, how many objects are dropped, things like that. And we've thought quite a bit about that. And on the second side, there's more on the classification side. And I think there's a lot of room to talk about how we choose to make the rankings based on that. And the second thing I wanted to mention is that one thing we are thinking about is how Plastic will ingest all the information from the brokers. And I think this is a side conversation that has been brought up in the previous meeting. I'm not sure how much has been talked about in this meeting, but is about standardization of outputs from brokers in terms of alert streams, also API queries. So it'd be really helpful for us if the broker teams could organize themselves and have some standards in terms of alert streams, outputs, so that we can more easily ingest information from you. So that's it.
If I'm not mistaken, I don't know if Francisco maybe wants to comment, but that was discussed on the Thursday in one of the parallel.
Yes, a little bit. Yeah.
So it's in the notes, I guess, correct?
Yeah, and I think looking at the notebooks, we see that we are kind of converging, I would say.
Okay, so thank you very much. I think this was a really interesting discussion, but we should probably stop and take a 5-minute break before we resume with the discussion. So thanks a lot for the really nice tutorials and for the discussion, and see you in 5 minutes.